Newton's second law, force and acceleration. Newton's second law of motion, mass and acceleration. State the relationship between acceleration and net force. State the relationship between acceleration and mass. State and explain Newton's second law of motion. List the factors that affect the force of friction between surfaces. Distinguish between force and pressure. Explain why the acceleration of an object in freefall does not depend upon the mass of the object. List the factors that affect the air resistance force on an object. The big idea. The object accelerates when a net force acts on it. In Chapter 2, we discussed the concept of mechanical equilibrium. The sum of the forces equals zero, which means that forces are balanced. In Chapter 3, we extended this idea to the law of inertia, again with balanced forces. In this chapter, we consider what happens when forces aren't balanced, when the net force is not zero, when an object is not in equilibrium. The net force on a kicked football, for example, is greater than zero, and the ball accelerates. Its path through the air is not a straight line, but curves downward due to gravity, again, an acceleration. Most of the motion we see undergoes change. This chapter covers changes in motion, accelerated motion. We learn that acceleration describes how quickly velocity changes. It's the change in velocity per unit time. Specifically, it is the change in velocity per unit time. Recall the definition of acceleration. Acceleration equals change in velocity divided by time interval. We will now focus on the causes of acceleration. Force. Forces cause acceleration. Discover, what effect does air resistance have on falling objects? 1. Use a stopwatch to determine the time required for a single coffee filter to fall 1 meter. Determine the time required for 4 coffee filters nested inside one another to fall 2 meters. Determine the time required for 9 nested filters to fall a distance of 3 meters. If possible, measure the time of fall for 16 nested filters dropped from a height of 4 meters. Analyze and conclude. Observing. What did you observe about the motion of a single filter as it fell? Did it appear to accelerate? Or did it move with a constant velocity? How did the time of fall compare for each of the 4 trials? Predicting. How long do you think it would take for 25 nested coffee filters to fall through a distance of 5 meters? Making generalizations. What determines the speed of similarly shaped objects falling under the influence of gravity and air resistance? 6.1. Force causes acceleration. Consider an object at rest, such as a hockey puck or perfectly smooth ice. The forces on it, gravity and the support force, are balanced, so the puck is in equilibrium. Hit the puck, that is, apply an unbalanced force to it, and the puck experiences a change in motion. It accelerates. When the hockey stick is no longer pushing it, there are no unbalanced forces, and the puck moves at constant velocity. Apply another force by striking the puck again, and the puck's motion changes again. Unbalanced forces acting on an object cause the object to accelerate. Most often, the force we apply is not the only force acting on an object. For example, after the boy kicks the football in figure 6.1, both gravity and air resistance act on the football. Recall from the previous chapter that the combination of forces acting on an object is the net force. Acceleration depends on the net force. To increase the acceleration of an object, you must increase the net force acting on it. 6.1. Kick a football and it neither remains at rest nor moves in a straight line. Double the force on an object and its acceleration doubles. If you triple the force, its acceleration triples. We say an object's acceleration is directly proportional to the net force acting on it. We write acceleration is proportional to net force. The symbol tilde stands for is directly proportional to. Concept check. What causes an object to accelerate? Force, force, force. Let's look at 6.2. 6.2, mass resists acceleration. Push on an empty shopping cart. Then push equally hard on a heavy, loaded shopping cart. As shown in figure 6.2, the loaded shopping cart will accelerate much less than the empty shopping cart. Acceleration depends on the mass being pushed. For a constant force, an increase in the mass will result in a decrease in the acceleration. The same force applied to twice as much of the mass results in only half the acceleration. For 3 times the mass, 1/3 the acceleration results. 6.2, the acceleration produced depends on the mass that is pushed. In other words, for a given force, the acceleration produced is inversely proportionate to the mass. The relationship can be written as an equation. Acceleration is inversely proportionate to the mass. Inversely means that the two values change in opposite directions. Mathematically, we see that as the denominator increases, the whole quantity decreases by the same factor. Concept check. How does an increase in mass affect acceleration? 6.3, Newton's second law. Newton was the first to realize that acceleration produced when we move something depends not only on how hard we push or pull, but also on the object's mass. He came up with one of the most important rules of nature ever proposed, his second law of motion. Newton's second law describes the relationship among an object's mass, an object's acceleration, and the net force on an object. F equals ma. Here is inversely proportionate and directly proportional. So y equals 1 over x and xy equals 1. That's an inversely proportional relationship. And y over x equals 1 or y equals x, that is proportionate. Newton's second law states that the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force is in the same direction as the net force and is inversely proportionate to the mass of the object. This relationship can be written as an equation. Acceleration is proportional to the quotient, net force over mass, or simply F equals ma. Figure 6.3, the great acceleration of the racing car, or in this case the space shuttle, is due to its ability to produce large forces. By using consistent units such as newtons, N, for force, kilograms, kg for mass, and meters per second squared for acceleration, we get the exact equation. Acceleration equals net force over mass. In briefest form, where A is acceleration, F is net force, and m is mass, A equals F over m, or simply F equals ma. The acceleration is equal to the net force divided by the mass. From this relationship, we see that doubling the net force acting on an object doubles its acceleration. Suppose instead that the mass is doubled. Then acceleration will be halved. If both the net force and the mass are doubled, the acceleration will be unchanged. Concept check. What is the relationship among an object's mass, an object's acceleration, and the net force on an object? Discover. Acceleration. Which way? Pull a spool of thread horizontally to the right by the thread. The thread should be at the bottom of the spool. Which direction does the spool roll? Repeat step 1 with the thread on the top of the spool. Which direction does the spool roll? Are the net force on the object and an object's acceleration always in the same direction? Why? And here is a picture of the spool. A car has a mass of 1,000 kilograms. What is the acceleration produced by a force of 2,000 newtons? So that's going to be 2 meters per second squared if you follow the calculations there. I don't want to get too bogged down on reading what you can easily read yourself. You can use Newton's second law to solve the car's acceleration. If the force is 4,000, what is the acceleration? Well, it'll be 4,000 divided by 1,000, or 4 meters per second squared. Doubling the force on the same mass simply doubles the acceleration. Physics problems are often more complicated than these. We don't focus on solving complicated problems in this book. Instead, we emphasize equations as guides to thinking about the relationships of basic physics concepts. The plug and chug problems at the ends of many chapters familiarize you with equations, and the think and solve problems go a step or two further for more challenge. Solving problems is an important skill in physics, but first learn the concepts. Then problem solving will be more meaningful. How much force or thrust must a 30,000 kilogram or 30,000 kilogram jet develop to achieve an acceleration of 1.5 meters per second squared? If you know the mass of an object in kilograms and its acceleration in meters per second, then the force will be expressed in newtons. 1 newton is the force needed to give a mass of 1 kilogram and acceleration of 1 meter per second squared. You can arrange Newton's second law to read force. That is, force equals mass times acceleration, or F equals ma. So 30,000 kilograms times 1.5 is going to be 45,000 newtons, or 45,000 kilogram meters per second squared. The dot between kg and m over s squared means that the units are multiplied together. So kg dot m over second squared is actually read kilogram meters per second squared, or simply F equals 45,000 newtons. If a car can accelerate to 2 meters per second squared, what acceleration can it attain if it is towing another car of equal mass? A point to ponder. Remember, F equals ma. The same force on twice the mass produces half the acceleration, or 2 meters per second squared. 6.4, friction. Friction is a force like any other force and affects motion. Friction acts on materials that are in contact with each other, and it always acts in a direction to oppose relative motion. When two solid objects come into contact, the friction is mainly due to irregularities in the two surfaces. When one object slides against another, it must either rise over the irregular bumps or else scrape them off. Either way requires force. The force of friction between the surfaces depends on the kinds of material in contact and how much the surfaces are pressed together. Friction. Excellent. Think. Two forces act on a book resting on a table. Its weight and the support force from the table. Does a force of friction act as well? No, not unless the book tends to slide or does slide across the table. For example, if it is pushed toward the left by another force, then friction between the book and the table will act to the right. Friction forces occur only when an object tends to slide or is sliding. More about this in the Concept Development Practice book. For example, rubber against concrete produces more friction than steel against steel. That's why concrete road dividers have replaced steel rails. The friction produced by a tire against the concrete is more effective in slowing the car down than friction produced by a steel car body sliding against a steel rail. Notice in figure 6.4 that the concrete divider is wider at the base to ensure that the tires of the side-swiping car will make contact with the divider before the steel body does. Friction is not restricted to solids sliding or tending to slide over one another. Friction also occurs in liquids and gases. Both liquids and gases are called fluids because they flow. Fluid friction occurs as an object pushes aside the fluid it is moving through. Have you ever tried running a 100-meter dash through waist-deep water? 6.4. A concrete road divider has a better design than a steel road divider for slowing an out-of-control side-swiping car. The friction of liquids is appreciable, even at low speeds. Air resistance is the friction acting on something moving through the air. Air resistance is a very common form of fluid friction. You usually don't notice air resistance when walking or jogging, but you do notice it at higher speeds that occur when riding a bike or skiing downhill. When friction is present, an object may move with a constant velocity even when an outside force is applied to it. In such a case, the friction force just balances the applied force. The net force is zero, so there is no acceleration. For example, in figure 6.5, the crate moves with a constant velocity when the force pushing it balances the force of friction. Let's take a look at 6.5. The direction of the force friction always opposes the direction of the motion. A. Push the crate to the right and friction acts towards the left. B. The sack falls downward and air friction acts upward. The sack will also fall with a constant velocity once the force due to air friction balances the sack's weight. A diagram showing all the forces acting on an object is called a free body diagram. Concept check. What factors affect the force of friction between surfaces? The first automobiles were little more than horse carriages with engines. Over time, engineers came to realize that by reducing the frontal surface of cars and eliminating parts that stick out, the air resistance force on a car could be reduced. When a car cruises at a constant speed, the net force on the car is zero. This is linked to technology, automobile design. By lowering the air resistance force at any speed, the amount of force needed by an engine is reduced, meaning better fuel economy. Over the years, cars have gotten slicker with teardrop-shaped bodies and teardrop-shaped around side mirrors. Door handles are set into the doors. Even wheel wells and the undersides of cars have been smoothed. Automotive engineers use computers to design cars with less air resistance and use wind tunnels to measure the car's air resistance. 6.5. Applying force, pressure. Look at figure 6.6. No matter how you place a book on a table, the force of the book on the table is the same. You can check this by placing a book in any position on a bathroom scale. You'll read the same weight in all cases. Balance a book in different positions on the palm of your hand. Although the force is always the same, you'll notice differences in the way the book presses against your palm. These differences are due to differences in the area of contact for each case. For a constant force, an increase in the area of contact will result in a decrease in the pressure. Figure 6.6. The upright book exerts the same force, but greater pressure against the supporting force. The amount of force per unit area is called pressure. More precisely, when the force is perpendicular to the surface area. Pressure equals force divided by area of application. In the equation form, P equals F over A, where P is the pressure, A is the area for which the force acts. Force, which is measured in newtons, is different from pressure. Pressure is measured in newtons per square meter, or pascals, PA, named after a gentleman by the name of Pascal. 1 Newton per square meter is equal to 1 Pascal. You exert more pressure against the ground when you stand on one foot than when you stand on both feet. This is due to the decreased area of contact. Stand on one toe like a ballerina and the pressure is huge. The smaller the area supporting a given force, the greater the pressure on that surface. You can calculate the pressure you exert on the ground when you are standing. One way is to moisten the bottom of your feet with water and step on a clean sheet of graph paper. Count the number of squares on the graph paper contained within your footprint. Divide your weight by this area and you'll have the average pressure you exerted on the ground when standing on 1 foot. How will the pressure compare with the pressure you exert when you stand on 2 feet? A dramatic illustration of pressure is shown in figure 6.7. The author applies appreciable force when he breaks the cement block with a sledgehammer. Yet his friend, the author of the lab manual, sandwiched between 2 beds of sharp nails, is unharmed. The author applies a force to fellow physics teacher Paul Robinson, who is bravely sandwiched between beds of sharp nails. The driving force per nail is not enough to puncture the skin. Caution, do not attempt this on your own. The friend is unharmed because much of the force is distributed over the more than 200 nails that make contact with his body. The combined surface area of this many nails results in a tolerable pressure that does not puncture the skin. Caution, this demonstration is quite dangerous. Do not attempt it on your own. How does the area of contact affect the pressure of force exerted on an object? In attempting to do the demonstration shown in figure 6.7, would it be wise to begin with a few nails and work upward with more nails? I wouldn't suggest that. Why would that be? The more the nails, the better it is, and the less harm will be caused. No. There would be one less physics teacher if the demonstration were performed with fewer nails. The resulting greater pressure would cause harm. 6.6. Freefall Explained. Recall that free fall occurs when a falling object encounters no air resistance. Also recall that Galileo showed that falling objects accelerate equally regardless of their masses. This is strictly true if air resistance is negligible, that is, if the objects are in free fall. It is approximately true when air resistance is very small compared with the mass of the falling object. For example, a 10-kilogram cannonball and a 1-kilogram stone dropped from an elevated position at the same time will fall together and strike the ground at practically the same time. This experiment, said to be done by Galileo from the Leaning Tower of Pisa and shown in figure 6.8, demolished the Aristotelian idea that an object that weighs 10 times as much should fall 10 times faster than the lighter objects. Galileo's experiment and many others that showed the same result were convincing, but Galileo couldn't say why the accelerations were equal. The explanation is a straightforward application of Newton's second law and is the topic of the cartoon Backyard Physics. Let's treat it separately here. Recall that mass, a quantity of matter, and weight, the force due to gravity, are proportional. A 2-kilogram bag of nails weighs twice as much as a 1-kilogram bag of nails. Figure 6.8. In Galileo's famous demonstration, a 10-kilogram cannonball and a 1-kilogram stone strike the ground at practically the same exact time. Backyard Physics. If I drop the bag of clothespins and a single pin at the same time, which will fall to the ground first? That's easy. The bag of clothespins is heavier, which means gravity pulls on it with more force. So the bag of pins will accelerate more and hit the ground first. All right, that's what they think. So let's see what happens. Not true. The bag of clothespins has more mass, which is to say has more inertia. It will be less responsive to gravity and lag behind the single pin. So the single pin will hit the ground first? Very curious. Sorry gang, a tie score. How come? Since the bag has both a greater weight and a greater inertia, one offsets the other. Weight over mass is the bag, and less weight and less mass, the pin, they both equal g. The accelerations are equal, of course. So a 10-kilogram cannonball experiences 10 times as much gravitational force, weight, as a 1-kilogram stone. The followers of Aristotle believe that the cannonball should accelerate at a rate 10 times that of the stone, because they considered only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. A little thought will show that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller mass. Note, remember that only a single force acts on something in free fall, the force due to gravity. In symbolic notation, little f over little m equals big F over big M, where F stands for the force, weight acting on the cannonball, and M stands for the correspondingly large mass of the cannonball. The small f and m stand for the smaller weight and smaller mass of the stone. As figure 6.9 shows, the ratio of weight to mass is the same for these or any objects. All freely falling objects undergo the same acceleration at the same place on Earth. In Chapter 4, we introduced the symbol g for the acceleration. We can show the same result with numerical values. The weight of 1 kilogram stone is 10 newtons at Earth's surface. Figure 6.9, the ratio of weight, F, to mass, M, is the same for the 10 kilogram cannonball and the 1 kilogram stone. large F over large M equals small f over small m. The force acting on the falling object is the force due to gravity, the object's weight. Using Newton's second law, the acceleration of the stone is A equals F over M, weight over mass, 10 newtons over 1 kilogram, and then 10 kilogram meters over s squared over 1 kilogram equals 10 meters per second squared, that equals g. And acceleration of the cannonball is the same thing. You simply have a larger force, but you also have a larger mass. So they both equal g. In the famous coin and feather in a vacuum tube demonstration discussed in Chapter 4, the reason for an equal acceleration was not discussed. Now we know why the acceleration of the coin and the feather are the same. Notes: when the force of gravity and air resistance act on a falling object, it is not in free fall. All freely falling objects fall with the same acceleration because the net force on the object is only its weight, and the ratio of the weight to mass is the same for all objects. Why do all freely falling objects fall with the same acceleration? 6.7. Falling and air resistance. The feather and coin fall with equal accelerations in a vacuum, but very unequal in the presence of air. When falling in air, the coin falls quickly while the feather flutters to the ground. The force due to air resistance diminishes the net force acting on the falling objects, speed, and area. The force due to air resistance is experienced when you stick your hand out the window of a moving car. If the car moves faster, the force on your hand increases, indicating that air resistance force depends on speed. Which experiences a greater air resistance force? A falling piece of paper or a falling elephant? The elephant. It has a greater frontal area and falls faster than a piece of paper, both of which mean the elephant pushes more air molecules out of the way. The effect of the air resistance force on each, however, is another story. If instead of just your hand, you hold your physics book out the window with the large side facing forward, exposing maximum frontal area for the book, the air resistance force is much larger than it was on your hand at the same speed. You find that the force of the air resistance is also proportional to the frontal area of the moving object. The air resistance force an object experiences depends on the object's speed and area. How does air resistance affect the motion of falling objects? Drop a sheet of paper and a book side by side at the same time. Does either of them hit the ground first, or do they land at the same time? Place a piece of paper against the bottom surface of the horizontally held book. Drop them both at the same time. Does either of them hit the ground first, or do they hit the ground at the same time? Repeat step 2 with a piece of paper on top of the book. Explain the effect of air resistance on the motion of the piece of paper and the book, steps 1 through 3. An expression describes the relationship between speed, area, and air resistance. Air resistance force equals speed times frontal area. The expression shows that the air resistance force is directly proportional to the speed and frontal area of an object, terminal speed. When the air resistance force on an falling object, like the skydiver shown in figure 6.10, builds up to the point where it equals the weight of the object, then the net force on the object is 0 and the object stops accelerating. Figure 6.10, skydivers reach terminal speed when air resistance equals weight. We say that an object has reached its terminal speed. Terminal speed is the speed at which the acceleration of an object, falling object, is 0 because friction balances the weight. If we are concerned with direction, which is falling for falling objects, we say it has reached its terminal velocity. Terminal velocity is terminal speed together with the direction of motion. A falling feather reaches its terminal speed quite quickly. Its area is large relative to its very small weight. Even at small speeds, the air resistance has a large effect on the feather's motion. A coin, however, has a relatively small area compared to its weight. So the coin will have to fall faster than a feather to reach its terminal speed. Think. If a heavy person and a light person open their chutes together at the same time, and each wears the same size parachute, who will reach the ground first? The heavy person will reach the ground first. Like a feather, the light person reaches terminal speed sooner, while the heavy person continues to accelerate until a greater terminal speed is reached. The heavy person moves ahead of the light person, and the separation continues to increase as they descend. The terminal speed for a skydiver varies from about 150 to 200 kilometers per hour, depending on the weight and orientation of the body. A heavier person will attain a greater terminal speed than a lighter person. The greater weight is more effective in plowing through air. Body orientation also makes a difference. It's important to emphasize that zero acceleration does not mean zero velocity. Zero acceleration, that the object will maintain the velocity it happens to have, neither speeding up nor slowing down, nor changing direction. More air is encountered when the body is spread out and surface area is increased, like that of a flying squirrel in figure 6.11. Terminal speed can be controlled by variations of body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like a flying squirrel, while the light person falls head first or feet first. A parachute greatly increases air resistance and cuts the terminal speed around to 15 to 25 kilometers per hour, slow enough for a safe landing. If you hold a baseball or a tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. Figure 6.11, the flying squirrel increases its area by spreading out. This increases air resistance and decreases the speed of its fall. Skydivers and flying squirrels are not alone in increasing their surface area when falling. When the paradise tree snake jumps from a tree branch, it doubles its width by flattening itself. It acquires a slightly concave shape and maneuvers itself by undulating in a graceful S shape, traveling more than 20 meters in a single leap. But if you drop them from the top of a building, you'll notice the heavier baseball strikes the ground first. This is due to the buildup of air resistance at higher speeds. At lower speeds, air resistance is often negligible, but at high speeds, it can make quite a difference. The effect of air resistance is more pronounced on the lighter tennis ball than on the heavier baseball. So it accelerates. So the acceleration of the fall is less for the tennis ball. The tennis ball behaves more like a parachute than a baseball does. Figure 6.12 shows that a golf ball has a greater acceleration falling in air than a foam ball. When Galileo reportedly dropped the objects of different weights from the Leaning Tower of Pisa, the heavier object did get to the ground first. The stroboscopic photo shows a golf ball and a foam ball falling in air. The heavier golf ball is more effective in overcoming air resistance, so its acceleration is greater. However, the time difference was only a split second, rather than pronounced time difference expected by the followers of Aristotle. The behavior of falling objects was never really understood until Newton announced his second law of motion. Isaac Newton truly changed our way of seeing the world by showing how concepts connect to one another. The connection between acceleration, force, and mass, discovered by Newton in the late 1600s, led to men landing on the moon in the 1900s. Newton's second law was primarily responsible for this feat. What factors determine the air resistance force on an object? Summary: Newton's second law of motion, mass, and acceleration. Unbalanced forces acting on an object cause the object to accelerate. For a constant force, an increase in the mass will result in a decrease in the acceleration. Newton's second law states that the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, is the same direction as the net force, and is inversely proportional to the mass of the object. The force of friction between two surfaces depends on the kinds of material in contact and how much the surfaces are pressed together. For a constant force, an increase in the area of contact will result in a decrease in pressure. All freely falling objects fall with the same acceleration because the net force on an object is only its weight, and the ratio of weight to mass is the same for all objects. The air resistance force on an object depends on the object's speed and area.